Everyone, welcome back to another lesson in MCV4U. Today we'll be looking at matrices and the Gauss-Jordan method. And so a matrix is a rectangular array of numbers. And so here we see that then we have 5 and 2, 1 and -3, 4 and 0. And that represents a 2 by 3 matrix. The first number will represent the number of rows in the matrix. And then the second number will represent the number of columns. And so here we see that we have a 2 by 2 matrix, again means 2 rows, 2 columns. A 1 by 2 matrix, again, would represent 1 row and 2 columns. And then finally, here a 2 by 1 matrix would represent, again, 2 rows and 1 column. So here if we see that we have a system of equations, we have x plus 2y plus 2z is equal to 9. We have x plus y is equal to 1. And we have 2x plus 3y minus z is equal to 1. So we want to take this system of equations and convert it into our matrix form. And so here we're going to label the first equation as row 1, label our second equation as row 2, and we'll label our third equation as row 3. And so the coefficients that are in front of the x, y, and z value will represent our columns. So here, in column number 1, that will be the coefficients of x. Column number 2, that's the coefficients for y. And then column number 3 are the coefficients of z. Okay, so based on that, now we can write it in, again, given the system, in coefficient matrix form. So when we're writing it in coefficient matrix form, then in column number 1, again, that represents all the coefficients of x in our system of equation. So here that would be 1, 1, and 2. In our second column, that represents all the coefficients of y. Here that's 2, 1, and 3. And then in our third column, that represents all the coefficients of z, which here are 2, 0, and -1. Okay, so that's in our coefficient matrix form. In our augmented matrix form, we're going to add the constants that are on the equal side, on the right side of the equal sign. So here we have 1, 1, and 2, so same coefficients here. 2, 1, and 3, and 2, 0, and -1. However, what we're going to do now is we're going to add this line, which represents the equal sign in each of the rows, and we're going to write our constants. So here we have 9, 1, and 1. And so here, this represents, again, the equal sign. This represents the equal sign in each row. Okay, and what our goal is we want to get it into this particular form, which is called the row echelon form or Gaussian elimination. And so our goal is to get it so that we produce the diagonal of 1s, so we see that's highlighted there, and 0s in the subsequent positions below. So again, our goal is to produce the diagonal of 1s and 0s in the subsequent position below. So again, 0s in the position in the second and third row, and 0 in the y position in the third row. And here, just a note, technically we do not need a 1 in the z position in the third row, since that number represents the coefficient of z, and we can simply take or solve for the z value from the third row And so here the example would be 5z is equal to -10, because then there's no x or y values here because those would be 0. And so here, example number 1 says use elementary row operations from row echelon form to solve the above system of equations. Okay, so let's redraw our matrix here. So if we redraw our matrix, then we have 1, 1, and 2, and then we have 2, 1, and 3, and then 2, 0, and -1, and our constants would be 9, 1, and 1. Again, column 1 represents the coefficients of x, column 2 represents the coefficients of y, column 3 represents the coefficients of z. And so here, if we look at this, right now we have our 1 here, which is good at the column 1 and row 1 position. But we see here that in our column 1, row 2, and row 3 position, those, if we try to make those in the form, should be 0. And so how we do that is for row number 2, so for row number 2, I'm going to take row 2 and we'll subtract it by row 1. Right, so row 2 subtracted by row 1, so 1 minus 1, which gives us 0. And here for row 3, again, we'll take row 3 minus 2 of row 1 to get that to 0 as well. Okay, so here what that leaves us with is we'll be left with 1, 0, and 0. We have 2, negative, 2, -1, and -1. And we have 2, -2, and -5. And then for our coefficients, we'll be left with 9, -8, and -17. And that's all from, again, taking our row 2 and subtracting it by our row 1. And in row 3, we took our row 3 subtracted by 2 of row 1. Okay, so now we got, again, our 1. In our first column, we got our 1, 0, 0, which is in that row echelon form. But again, we're still in terms of our column 2, row 2, we need to make that -1 into 1. And what you might have noticed here is that our row 1 has remained the same. That remains unchanged. And this is also called the control row. And the reason it's called the control row is because it has all 3 variables. Okay, so now our goal here is to change, again, our column 2, row 2, into, again, positive 1. So here, if we look at our row 2, we're going to take row 2, and we'll multiply that by -1. And so here, now if we look at our new matrices after doing that, we have, again, 1, 2, 2, and 9, In our second row, it's 0, 1, 2, and 8. And in our third row, we have 0, -1, -5, and -17. And so here, again, our next step here is to then make that -1 into 0. And so here what we can do is we can take our row 2 and add that to row 3. So here we'll take row 2 and add it with row 3. So that will give us, here we have 1, 0, and 0. We have 2, 1, and 0. We have 2, 2, and -3. And our constants here will be 9, 8, and -9. Okay, so here we, again, in our third row, we have 0, 0, -3, and -9. And what we can do here is we can, again, take our row 3 and we'll divide that by -3. Again, to get this column 3, row 3, 2, 1. As well, what we see here is we can find our z value. So here, if we take this here, we see that -3z is equal to -9, which means that, again, z will be equal to 3. So here, if we look at, again, our Gaussian elimination, so here are, when we draw that matrices, again, here we get 1, 0, and 0. We have 2, 1, and 0. And we have 2, 2, and 1. And so here we see that we have the ones that are across, and we have, again, our zeros in these positions. And here, if we have our line representing our equal sign, those equal to 9, 8, and 3. So here, again, remember column 1, x, y, and z. And again, here, really, again, these are, again, x, y, and z. And here, these are y and z. And here are z. And these are all equal. Okay, so here, again, we know that z is equal to 3. So we found that from below as well. But here we see that, again, z is equal to 3. In row 2, here we can get that y plus 2 times z, which is 2 times 3, is equal to 8. And so y is equal to 2. And then from row 3, here we can get that x plus 2y, which is 2 times 2, x plus 4, plus 2 times 3, which is 6, is equal to 9. So here, x is equal to -1. Okay, so here, again, our Therefore, our point of intersection will be -1, 2, and 3. Okay. So again, the Gauss-Jordan method. Again, the Gauss-Jordan method requires us to reduce all matrices to the reduced, again, row echelon form. So as we see here, again, this is, again, X, Y, and Z. Again, those are all the 1 values that are across. And here we see that at the last row, it's 0, 0, 1, and then the constant value. And so here what that means is, again, X is equal to A, Y is equal to B, and Z is equal to C. And so here it says, write the matrix, again, from example 1 in reduced row echelon form. So here we have our 1, 0, 0, 2, 1, 0, 2, 2, -3, and 9, 8, and -9. Here we'll take our row 3, and we'll divide that by -3. And what that will give us is will give us 1, 0, and 0, 2, 1, and 0, 2, 2, and 1. And just move this a little bit. So we have 2, 2, and 1, and then we have 9, 8, and 3. From there, again, we can take our row 2 and subtract that by. So here we'll take our row 2 and we'll subtract it by 2 row 3. And so here what we'll be left with is 1, 0, and 0. And then we have 2, 1, and 0. And we have 2, 0, and 1. And 9, 2, and 3. And so here in this one, we simplified, again, that 2 value to make it 0. Next, again, we're going to simplify this 2 value to make that 0 as well. And so to do that, we're going to take our R1 subtracted by 2, R2. Take, again, our row 1 subtracted by 2 of the row 2. And then that will leave us with 1, 0, 2, and 5. And the rest we keep the same. So 0, 0, 1, 0, 0, 1, and then 2 and 3. And here, next thing we have to simplify is this 2 value here. Okay, so here we can take our R1 and subtract that by 2, R3. And so that will provide us with our simplified, again, or reduced row echelon form. And so that will be in our row 1, 1, 0, 0, and 1, and -1. Row 2, we have 0, 1, 0, and 2. And row 3, we have 0, 0, 1, and 3. And again, this represents our x value, this represents our y value, and this represents our z value. So therefore here, our point of intersection will be -1, 2, and 3. Okay, so example number 3 says, again, determine the solution of the following system. So here we have our matrices, again, 0, 1, 0, 0, 0, 1, -1, 2, and 0, and 4, 0, -1. What we notice here is that, again, at the top, this is actually our z row. And so what we want to do is we want to take our row 1 and we're going to move it to row 3. Our row 2 will become our row 1, and our row 3 will become our row 2. So if we rewrite this, we'll get 1, 0, and 0. We have 0, 1, and 0. We have 2, 0, and -1. And we have 0, -1, and 4. So we just again rewrote that. Again, here we have our x and our z, again, value here. And so here of our z value here at the very end. So what we know is we know that -z is equal to 4, which means that z is equal to -4. From that, we can take our equation. We also know here in our second row that y is equal to -1. And so here we can take our initial equation to find x. So here we have 1x plus 2 times z, which is -4, is equal to 0. And so here x is equal to 8. So therefore, our point of intersection will be at 8, -1, and -4. Okay, example number 4 says, again, use the Gaussian elimination to solve the following. Okay, so here we have x minus y plus 2z is equal to -7. X minus y plus 2z is equal to -7 is our second equation, and our third equation is x plus 2y minus z is equal to 6. Okay, so here, if we use our Gaussian elimination, so we're going to draw our matrices. Okay, column number 1, our x values, 1, -1, and 1. Column 2, our y values, -1, -1, and 2. And then column 3, 2, 2, and -1. And then our constants, -9, -7, and 6. And so here we have -1 and 1. And so here we'll take row 2 and add that to row 1 to make that equal to 0. And here for row 3, we'll take row 3 subtracted by row 1. And so here, that will leave us with 1, -1, 2, and -9. Remember that first row stays the same. And so here we have 0, 0, -2, 3, 4, -3, and then -16 and 15. Here what we can do is we can take our row 2 and we'll divide that by -2, and we'll take row 3 and we'll divide that by 3. And so here we have 1, 0, and 0. We have -1, 1, and 1. We have 2, -2, and -1. And for our constants, we have -9, 8, and 5. And so here we have to make this value of 1 equal to 0. So here we'll take our row 3 and subtract that by row 2. So that'll give us 1, 0, -1, 1, 2, and -2, and -8, 9, and 8. And then our bottom row will now be 0, 0, 1, and -3. Okay, so now it matches our Gaussian elimination or our row echelon form. And so here, again, we see that from our third row, we can find our value of z. So that z is equal here to -3. From our row 2, then we can find y. So 1y minus 2 times z, which is -3, is equal to 8. Therefore, y is equal to 2. And then subbing in everything into our first equation, so x minus -2 plus 2 times -3 will be equal to -9, and subbing in the values of y and z into that equation there. So here x will be equal to -1. And so here, therefore, our point of intersection will be -1, 2, and -3. Okay, so example number 5 says, can use Gaussian elimination to solve the following. So here we have x minus 3y minus 2z is equal to -9. 2x minus 5y plus z is equal to 3, and -3x plus 6y plus 2z is equal to 8. Okay, so here let's write our matrices. So here we have 1, 2, -3, column number 2, -3, -5, and 6, and -2, 1, and 2, and our constants being -9, 3, and 8. Okay, so first thing we're going to do is we're going to, again, simplify, again, the column 1, row 2, and row 3. So here we'll take, for row 2, we'll take row 2 subtracted by 2 of row 1 to make that 2 to 0. And for row 3, we'll take row 3 plus 3 of row 1 to make the -3 to 0. And so here we have 1, -3, -2, and -9. Now these two values are 0. These values would be -1, -3, 5, -4, and then 21 and -19. Here we need to make this value of -3 to 0. And we'll do that by taking row 3 plus 3 of row 2. That'll give us 1, 0, -3, 1. These stay the same, -2 and 5. Constants being -9 and 21. Again, what's different here is our bottom row, which would be now 0, 0, 11, and 44. Okay, from this, we can see at the bottom that, again, our 11z is equal to 44. And so z is equal to 4. In terms of our second row, we have y plus 5 times z. So 5 times 4, which is 20, is equal to 21. And so here y is equal to 1. And then we can set both of those into our first row equation, which is x minus, again, 3 times y, which is -3, and -2 times z, which would be -8. So here we have x minus 3 minus 8 is equal to -9, and therefore x will be equal to 2. And so here, therefore, our point of intersection will be at 2, 1, and 4. Okay. So here, if we look at, again, a challenge problem. So here, there's 4 components. So we have x, y, z, and u now. So let's take a look at this. Okay, so we'll draw the matrices again. So we have, again, our 4 components. So here for the first column will be our x values, our coefficient for our x values. So 1, 2, 0, and 3. So this will be x. For y, that would be -1, 0, -1, and -3. So that would be for y. Third column for z, which will be -1, 2, -2, and -2. And then last one will be for u. And for u will be 1, 0, 0, and 4. And again, our constants are 0, 8, -8, and 7. Okay, so here we want to simplify, again, first our row 2 and our row, again, our row 4 here in this situation. So here we'll take row 2 and we'll subtract it by 2 of row 1. Okay, so get that value of 2 to 0. Here we will take our row 4 and subtract it by 3 of row 1. Okay, so again, that's to make this 3 equal to 0 as well. Okay, so our new matrices will look like this. So we have 1, -1, -1, 1, and 0 for our first row. Our second row, now we have 0, 2, 4, -2, and 8. Third row didn't change, so 0, -1, -2, 0, and -8. Then our last row, now we have as 0, 0, 1, 1, and 7. Okay. So here, next thing we want to do is we want to make this value of 2 to 1. And so here we'll take row 2 and we'll divide that by 2. So here we will have, again, our first row stays the same. Our second row now will be 0, 1, 2, -1, and 4. Our third row didn't change, so 0, -1, -2, 0, and -8. And our last row also stayed the same. So 0, 0, 1, 1, and 7. Okay, so here, the next thing we'll look here is we will try to make this -2 into 0, and you'll see in a second why we want to do that. And so here we'll take row 3 and add that to row 2 to make that 0. So here when we do that, what we get in terms of our matrices is we'll get 1, -1, -1, -1, 1, and 0. In row 2, 0, 1, 2, -1, and 4. In row 3, currently here, we have 0, -0, 0, 0, -1, and -4. And our last one, that stayed the same, which was 0, 0, 1, 1, and 7. And what you might notice here is that what we just changed in terms of row 3 looks like something that should be in the last row. So what we should do here is we're going to change the order. So we're going to change the order between row 3 and row 4. Okay, so if we rewrite that based on the change, what we'll have is we'll have 1, 0, 0, 0, -1, 1, 0, and 0, -1, 2, 1, and 0, and we'll have 1, and we'll have 1, -1, 1, and -1, and our constants will be 0, 4, 7, and -4. Okay, so when we change that order there, we notice a couple things. Okay, so here now we have, again, remember this is, again, x, y, z, and u. So here, if we look at this last row, you'll see that we can find our u value. So -u is equal to -4, and therefore u is equal to 4. From that, we can take our row 3 equation. Again, that's z plus our u value, so 4 is equal to 7. So here z is equal to 3. Then we can put that into our row 2 equation, which is y plus 2 times z, which is 2 times 3, minus u, which is minus 4, which is equal to 4. So here y is equal to 2. And then finally, the last equation we have here is, again, x minus, here again, our y times our -1, which would be minus 2, z times -1, which is -3, then plus u, 4, is equal to 0. So here x is equal to 1. And so here we get, therefore, x is equal to 1, y is equal to 2, z is equal to 3,
and U is equal to 4.